Hi, my name is Kurt Johnson, and today I'm going to show you how to use ColRadPy to calculate photon emissivity coefficients. So, as our previous examples with the ionization balance, we need to do some basic imports from Python, so NumPy, matplotlib. I'm going to specify where I have ColRadPy, so this is where I have ColRadPy, so you'll need to replace this to your directory with ColRadPy installed. The next thing is we are going to append the path of where ColRadPy is. And then what's different here is instead of from ColRadPy import ionization balance, we're just going to say import from ColRadPy, import ColRadPy. So the first thing I'm going to specify here is the file location. So for this example, we are using helium like oxygen. And so this is, I just have it in the same directory I'm going to run from. So that's why it's there. The next thing I'm going to specify is the temperature grid that I want to run on, the density grid I want to run on, and then what's different here from the ionization balance is I'm going to specify the number of metastables. So I can choose any level in the file to be metastable. However, for this example, I'm only going to say that the ground is considered metastable. And so the ground is at index 0, so that's why this is just an array of 1, 0. So this is the initial call to ColRadPy. So I need to specify the file location, give it the metastable array, then the temperature grid array, the density grid array. We need to tell ColRadPy to actually use ionization rates that are in the file, so this is true. The supplement with ECIP is going to make ECIP ionization rates anywhere in the file where there is not already, in the ADF04 file, anywhere where there is not already ionization rates. So this ECIP data is lower quality data, but it can be calculated for any level from within ColRadPy. For this example, we are only going to be using collisional excitation as well as ionization, so I'm turning off recombination rates from 3-body, and then also turning off recombination rates that are included in the ADF04 file. So this would be your radiative and dielectronic recombination. This last call here is telling ColRadPy that the interpolation of the collisional excitation rates are to be done with a cubic function. So you can put any function in here that SciPy1D interp will take. The first call to ColRadPy we're going to make here is we're going to tell it to make the excitation rates. So what this is going to do is it's going to interpolate on our temperature grid the rates from the ADF04 file and make those. The next thing it's going to do is it's going to interpolate the ionization rates from the ADF04 file on the temperature grid. This call actually makes the ECIP data for every level in the file. It then goes and supplements anywhere where there are not already ionization rates with this ECIP data. This function is going to actually populate the CR matrix. So this is going to take all of our rates that have been interpolated onto our temperature grid. It is then going to put them into the correct location in the matrix. This function here is going to take that matrix and solve it using the quasi-static approximation, and then also produce the derived quantities that are going to be of interest, such as the PEC in this example. This array is just a string label for the density grid up here that we're going to use in the legend. Here I'm just going to set up some plotting stuff that I think looks better than the defaults matplotlib, but this is personal preference. And so here is where we're actually going to start plotting things. So what I'm going to do is plot over all of the different density grid spots. And what I'm going to do is on the x-axis I'm going to put the temperature grid array, and then on the y-axis I'm going to put the photon emissivity coefficient here for the z line. So the way the PEC array works is it's index of the individual PEC, then the metastable index, or sorry, the metastable axis, then the temperature axis, and then the density axis. So I know from the levels in this file that the z line is going to correspond to the first PEC. You can also, I'll show some examples later of how to, if you didn't know exactly which PEC index corresponded to the Z-line, that you could figure this out. But here we'll just assume that we know it. Since we only have one metastable, the ground, we're only choosing the first index of the metastable array. We're plotting it against all of the temperatures, and then we're going to loop over the densities and plot each individual line. These next few are just plot decorations. We're then going to do the same thing for the X and Y lines. So because this file is only a term resolved file, the X and Y lines for a helium-like system are only going to show up as one PEC, and this is going to be the first PEC. Again, there are ways to go about finding this if you don't know it beforehand. And again, we're going to plot only the ground state contribution, all the temperatures, and then loop over the densities. Same thing again. And then this last one here is the W line, and it's going to look exactly the same as the other two. So if I run this, what we're going to see is we're going to see different trends from the PEC coefficient for the Z line, the X and Y lines, and then the W line. So if I go up to the top here, the Z line is going to be populated from the metastable state. It's, we didn't include it as a metastable, but it is actually technically a metastable level, which is why the PEC decreases with density. So because it's a PEC level, the Einstein A coefficient, or the spontaneous emission coefficient, down to the ground is going to be very small. So the excitation and de-excitation out of the level is actually producing a lot of the loss mechanisms. So as you increase your electron density, you're increasing the loss mechanisms out of this level, which is why the PEC actually goes down with density. So this is generally not what happens with PECs. So if we look at the X and Y lines here, we can see that they have the same trend with density that the Z line does. However, they now have a different density dependence because these levels are not metastable. The level that produces the X and Y line is not a metastable level, so the loss rate due to spontaneous emission is comparable or larger than the excitation and de-excitation rates, which is why it increases with electron density instead of decreasing. And we can see again that it has a very similar temperature dependence to the Z line. Now if we look at the W line, it has different, both a different density dependence than the other two lines, as well as a different temperature dependence. So we can see that it pretty much increases with temperature, drops off a little bit here towards the end, but not like the X and Y line as well as the Z line that increase sharply and then decrease with temperature. And then you'll also notice that the W line isn't really dependent on density, electron density. It's more or less constant. So we can take ratios of the Z, X, Y to the W line, and that would be temperature dependent.